Okay, hello everyone. So today we're gonna continue discussions on force. So you already saw one lecture, introduction to force and Newton's laws. So I'm gonna go over a couple of couple of different examples with numbers and see how force works in these different environments. All right, so okay, force examples. We already went over simple ones where you have a flat surface and you have an object here. We take this box, let's say the mass is m, and you are applying a force horizontally like this, the force F, and in these examples we're going to assume that there is no friction, right? It is just to make things simple for the time being. Later we will add friction, more realistic examples, but for right now we're going to take there is no friction. So you have an object, you apply a force. If there is no friction, there's nothing preventing it from moving. All you need is some force. It doesn't need to be a big force. Any force can move an object if there is no friction. The amount of acceleration is proportional to the force. So bigger the force, more acceleration you have. So we can write a relationship to connect force, mass and acceleration. It's Newton's second law, F equals ma. So we did bunch of examples using this. So I believe you all are familiar with this. So let's look at some variations of this. All right. Okay, so let me erase this whole thing. Where is it? Edit. Okay, so once again you have a flat surface, no friction, and there is a box. Let's say the box has mass m. You want to pull this to the side, to the right, but this time you're going to apply the force with some angle to the horizontal. Let's say angle here is theta. So you're applying a force F, making some angle. Still the object will move, right? It will start accelerating, but the acceleration will be a little different because now the force is not horizontal anymore. This force actually has two components. Now we can divide this into two components, right? We can divide this, like if you look at the force, if I draw it over here, force F, here's the horizontal line, here's the angle theta. We can divide this into, now you know what are the components are. We can make F cosine theta and F sine theta. So we can divide this into components. Now this horizontal component is what moving it to the right, right? This helps with moving to right. This one is trying to lift it. It's vertical, right? This sine component will try to lift the object. Now if the lifting force is big enough, if it is bigger than the weight of the object, it will raise it off of the ground. Otherwise it won't do anything. Object will still remain on the ground and will continue to move to the right. So F sine theta is kind of going to be a waste over here. It's not doing anything. But later we will see when we add friction, things get more interesting. But as of now, if f sine theta is not big enough to lift, nothing happens. F cosine theta will move this, will accelerate the object to the right. So f sine theta, we can say, will try to lift. Okay, all right. So let's put some numbers. No friction. Let's put some numbers. Let's say this mass is 100 kilograms and you're applying, oops, wrong. You're applying, let's say, 40 newtons with an angle of 30 degrees. What's the acceleration? Right, so let's assume that this is moving, well, let's do the numbers. So 40 newtons. So I'm going to divide this 40 newtons into components. Here's the angle 30. So we have 40 cosine 30, which is 40 cos 30. Let's see what that is. Probably already have the answer by now. 34.64. We will calculate this one also. 40 times sine 30. Actually, it's 20. Don't even need the calculator for that. This is 40 sine 30, which is 20. So we have a horizontal pulling force of 34.64 and a lifting force of 20 newtons. So if I redraw the diagram, 100 kg, we have 34.64 newtons. Now you don't need to draw this original 40 newtons or this angle or anything. We split the main force into components and it's trying to lift it with a 20 Newton force. That's not going to do anything. This object is 100 kilograms, so therefore weight is 100 times 9.81, 981 newtons. Unless you have something more than this, there's no way of lifting this, right? So this 20 Newton is kind of just not doing anything. All right, so what happens, let's see what happens to the acceleration. We're going to use F equals ma in this direction. So in the horizontal direction, force is 34.64, mass is 100 times acceleration. This gives you an acceleration of 34.64 divided by 100 equals 0.346 or 0.35 meters per second squared. All right, so when you have a force creating an angle, you split it into components and then use it with Newton's second law. Okay, let's look at another example. So I'm going to go ahead and clear this whole thing. All right. Actually, I should have done something before clearing it. Now, you guys can scroll back and go to the previous image, but let's say just a simple comparison. Same stuff, 100 kg. Now, in the previous problem, we had this 40 newtons like this. And we saw the acceleration, as I remember, 35 meters per second squared, right? The acceleration we got. Now, what if you apply this entire 40 newtons this way. I'm trying to show you what happens when there's an angle. Some of the useful force goes away because as the vertical component, which is right now not that useful. So instead of applying it with an angle, what if we make the whole thing horizontal? You can guess that the total, all these 40 newtons helping you with the acceleration, so you have a higher acceleration. Put F equals ma. This time you have the entire 40 newtons. So acceleration is 40 over 100 equals 0.4. So little bigger acceleration, right? Because the entire force is now helping with moving the object. Okay, so now I can erase this. Alright, here's another example. Example number 2. So we have the object sitting on a horizontal surface. Unless you apply a force either from this side or from the right, unless you apply a force, this thing is not gonna move. Things will remain at rest unless there's a net force, right? But now, instead of applying a force, I'm going to tilt this line. It's like placing something on an inclined surface. So here we have the box. Think about an occasion where you helping somebody with moving, right? Loading or unloading stuff from a truck. So you're gonna, like a U-Haul truck, so you have this ramp coming out from the truck, and you can place stuff like big drawers or washing machines, kind of heavy stuff, and on the ramp, and you can either push them up the ramp or push them down the ramp. So a similar situation. So the object is on an incline. Let's say the angle of this incline is theta with the horizontal. Now, if you think about that situation, let's say unloading from a U-Haul truck. You place some big box on the ramp, most probably it will just sit on that spot. It won't move unless you push it, because there is friction, right? There is friction. This object wants to slide down because its own weight, it's going to slide down, but friction is kind of preventing from sliding it down, right? Its friction is always an opposing force to the movement. So in this case, if there is friction, it might not move. But let's assume that there is no friction. Again, the simplest case, no friction. Later we will put friction. I've been telling this for some time now, so definitely sometime later you will see how friction works. Alright, so how do we mark the forces on a diagram like this, an inclined diagram? We call these diagrams where we mark the force, we call them force diagrams, right? Such a meaningful name, force diagrams. Or sometimes we call them free body diagrams. So it's pretty much the same thing. Some textbooks use free body diagrams. There is a extended meaning to this, but just for our understanding, it's a force diagram. Okay, so if let's go back to this simple case where the box is flat, on the surface is flat. So here's the mass. We know that we have mg, or the weight, pointing downwards. Now, when you place it on an incline, weight still points downward. That doesn't change, right? Weight is always towards the center of the earth. Gravity creates weight, therefore it's always towards the earth, so weight still going to point from the center, still going to point straight down, right? This is a straight line pointing downward, so this is your weight, or mg. Now what makes this thing slides down the ramp? We can divide this weight component, right? We can divide this vector into two components. This big vector, this weight, is divided into two components. Now to understand the situation, to explain what's going on here, we usually, like what you guys used to do is, like if you have a force going like this, we normally divide them into x and fy. If the force is this way, you can say this is your fx, this is your fy. If the force is pointing downwards, you call this is your fx, this is your fy, right? We used to split things into x and y components, horizontal and vertical component, for simplicity. There is no rule saying that you have to do it all the time. So in this case, again, to make things easier, we're gonna divide this weight vector, or this mg, into a parallel component and a perpendicular component. This one, the perpendicular component, it is perpendicular to the surface, right? It's 90 degrees to the surface. This one, parallel one, it's parallel to the surface, right? They're not x and y anymore, they're parallel and perpendicular components. So parallel to the plane, perpendicular to the plane. So we divide the main vector into parallel and perpendicular components. To do that, we need some angle. So using trig, we can show that if the incline has a theta degree with the horizontal, here's theta. This is an exercise for you. This same theta appears over here. I want you to work on this and figure out why there's a theta here. This angle becomes theta as well. So if I think you can see it, right? It's clear enough that this is the angle theta. Okay, let me make it a little bigger. So here's the incline, here's the box, this is the vertical line, parallel, perpendicular, theta is right here, that is theta. So using the angle, I can split this into, so let's forget this is W, let's just call it mg. I can split this into two components. The perpendicular one becomes mg cosine theta. Parallel one becomes mg sine theta. This is kind of similar to fx and fy, right? If you have a theta here, fx is f cosine theta, this is f sine theta. It's the same thing. It's a little tricky to see it here, why this one becomes cosine theta and this one becomes sine theta. One thing you can do is take this try to draw a vertical line. Take this thing, theta and mg, and rotate it until this guy and this guy falls onto x and y planes, and then you'll see it's pretty much like this situation or like this situation, right? You can, using this angle theta here, you can split it into cosine and sine. Same thing here. So the first thing we do is we split this big mg vector into two components. Now we have a parallel one, we have a perpendicular one. Now mg cosine theta, this is kinda like the weight of the object, but not the entire weight, a component of it. See over here, in this simple case, entire weight is pressing the object against the surface. So the surface creates the normal force, which is equals to mg. Now over here, not this big mg, not the entire mg, but mg cosine theta is pressing the object against the surface. This is what acting like a weight against the surface, right, against the plane. So we have a normal force pushing back. In this case, it's going this way against this mg cosine theta. Remember, I told you this in class also. Normal force, normal means perpendicular. It's always perpendicular to the surface it's coming from. So here we have a normal force that will cancel out mg cosine theta. So these two are equal to each other. They cancel out, similar to how these two forces cancel out each other. So the only unbalanced, only non-zero, non-cancelled force, or the net force, is this guy, mg sine theta. And this is what creates the acceleration down the ramp. The object will move down the ramp, so we can write Newton's equation this way, parallel to the ramp, F equals ma. Now we are going parallel to the ramp, right? Ramp is like this, object on it, so we are going to write force equation in the direction where it's moving. So F equals ma. So we have mg sine theta equals ma. So you see mass and mass cancels out. This gives you acceleration equals g sine theta. So this is an interesting result. If an object sliding down a ramp, or it could be sliding up a ramp. Let's start with sliding down the ramp. It's not on free fall anymore. It doesn't have the same free fall acceleration. Acceleration is a little less, g times sine theta. So it depends on the angle. If the angle is bigger, sine theta gets bigger, right? Acceleration gets bigger. If the angle is small, like if I draw it here, here's a very high incline. Theta is big, so sine theta also big. So g sine theta, or the acceleration, gets bigger. Here's one with a very small angle. Theta is small, sine theta also small. So small acceleration. Kind of makes sense, right? You place something here, you know that it's going to slide fast. Over here, it's going to be a slow acceleration. Alright? So, let's put some numbers and try an example. Okay, so I am going to erase this whole thing and I'm going to redraw that diagram over here. So here, theta, mass m, m, force is going to be mg sine theta. So let's put some numbers. Here we have the ramp. Let's say this box is 100 kilograms and the angle is 30. Question is, what is the acceleration? Acceleration down the ramp. What is the acceleration? It's sliding down the ramp. Alright. So what do? we find mg, which is 100 times 9.81 equals 981 newtons, and then we split this into mg cosine theta and mg sine theta. Now to find the acceleration down the ramp, we're going to write F equals ma this way down the ramp. It's always good to put an arrow pointing the direction so that we know, everybody knows which direction you are writing this Newton's second law. So F equals ma, we have mg sine theta equals ma, mass and mass cancels out, acceleration g sine theta equals 9.81 sine 30, so 4.5, 4.9, I think 9 some decimal point meters per second squared, right? Yep, that's it. That's how it works. Okay, so let's try another example. This time, okay, let's modify this same problem. So you have this box on the top of the ramp, and the ramp is 30 degrees, no friction. Remember, this is simple because there is no friction. Now if you put some friction here, there will be a force going against it, friction. So to find the net force for this equation, we have to subtract this friction from mg sine theta and then do a little modification here. But right now we're not going to worry about that. Okay, so here's the problem. The object is at the top of the ramp. The ramp is 5 meters long. Question is, what's the speed of the object at the bottom of the ramp? Speed at bottom. How fast it's moving. So you're gonna place the object here and you're gonna let it go. Let's say you are unloading something using a very slippery ramp, so you don't have to push anything, you just drop them on the ramp, they're just gonna slide down, and the speed is going to increase because it's accelerating, right? So in a problem like this, so here we have the ramp 5 meters long, making 30 degrees. So this 5 meters is measured along the ramp, not the height, it's the distance along the ramp. Starts here. So now we're gonna write kinematic equation. So kinematic equation in this direction, the direction where it's moving. It's not a free fall, not horizontal, not going up, it's going with the ramp, right? Parallel to the ramp. So the kinematic equation should be parallel to the ramp. So we start with V initial equals 0. We know that the distance, now everything's parallel, so all these numbers we plugging here should be parallel to the ramp. So parallelly it's going 5 meters. Acceleration, that also should be parallel to the ramp, 4.9. Speed at the bottom, we can use V final squared, V initial squared plus 2ax, 0 plus 2 times 4.9 times 5. V final squared equals 9.81 times 5, so that is like 48 something. So let's see what exactly the answer is. 49.05, 49.05 meters per second. Sorry, that's the square. So V final is square root of this is roughly around 7 meters per second. Okay. All right. So let's have you do this kind of problem. Okay, another thing real quick. Same problem. Here's the RAM. Let's say still 30 degrees. Let's say this thing is sitting there. Now it's gonna slide, right? Because there is no friction, this object is going to slide. How much force do you have to apply to prevent it from sliding? Let's say you're gonna push back on this. You're pushing back. Now let's say you're pushing back parallel to the ramp. This angle also matters. You can push it like horizontal like this. You can push it with a different angle, whatever angle you want. So the easiest way to do this is applying a force parallel to the ramp. So how much force do you need to prevent this from moving? Well, is it equal to the weight that something's wrong with the pen? Let me draw a new diagram. Okay, so here's this 100 kilograms, 30 degrees. The question is how much force you need to apply parallel to the ramp to prevent it from moving, sliding down. We know that the force acting downwards is mg sine 30. So the amount of force you need to apply is equals to that. So the force you need is mg sine 30, 100 times 9.81 times sine 30. So 981, 490, yeah, about 490 newtons. You need to apply in the opposite direction, in this direction, 490 newtons. Okay. All right, let's move on to another example. So I'm gonna erase this whole thing one more time. Okay, so let's go back to the simple horizontal plane. So here's the box, has mass m. Now you want to move this, so you can apply a force like this. You're pushing it, right? So you are directly in contact with the object. So if I draw a diagram with you in the picture of somebody, so here's a person trying to push this. So it's pushing, let's say pushing horizontally, right? Horizontal force. The person has to be in contact with the object. That's to push. You can do the same thing. You can attach something here, a rope or a string, and then you can pull it, right? You are applying a force this way. Same thing. You are applying, let's say you are applying 20 newtons here. You can do the same thing. You can pull on this rope with 20 newtons. Now this rope, this string, this thread, this will transfer that force. You are applying a force of 20 newtons. It's going to transfer that force. So this is like a medium that transmits force, right? Like, it doesn't need to be that complicated. You have done this before. You have pulled things using ropes, like think about pulling a big suitcase with its straps, something like that. So these kind of pulling forces, a force applied using a string or a rope. A force applied something like this, like a flexible material, like a not flexible, something that is not rigid. Well, that's also not the right way. A pulling force applied using something is called a tension. A tension force. Tension is always a pull. It can't be a push, right? You are only pulling. You can't push something with a string, right? It's going to collapse. So a pulling force transmitted along a string is called a tension. Now the rest of the math going to be same. Here you apply 20 newtons. Let's say the object is 100 kilograms, and we know that using F equals ma. 20 equals 100 times a, so acceleration will be 20 over 100 equals 0.2. Same thing here. You are applying 20, so the tension, I can mark it like this. We use the letter T, so we can say F equals ma. This tension becomes the force, right? You can even write instead of F, you can write T. That's fine, but normal standard is to use F. So 20 equals 100 times a, so you get the same 0.2, right? So just a new word, tension, a force applied using a string or a rope or a cable, right? So that's that. Now going back to this incline example, over here you applied, to prevent it from sliding, you applied 490 newtons, as I remember. You're pushing against it. You can do the same thing, same result. Object here, attach string and then pull the string. You are here, the same force. So now you are applying a tension of 490 newtons to prevent this object from sliding. If you apply more than that, you can accelerate this thing up the ramp. Okay? And also we can do so many variations to this problem. Like you can apply the tension over here parallel to the ramp, or you can make it some angle. So now it's, let's say, 20 degrees with the ramp. So now you have to think about the tension components. We can divide this. Oops, I kind of made it ugly. Hold on. We can divide this tension using this 20 degrees into a parallel component, T parallel, and a perpendicular component, T 90 degrees. And then continue your math, right? So there's so many things you can do with these components of forces. All right. Okay. We will work on a couple of examples in class, but now I'm moving on to another new topic. Another example. So I'm going to erase all this. All right. Let's go back to the simplest case. Here we have a box, and let's say this is 100 kg, and you are applying a horizontal force of let's say 50 newtons. So the question is, now it's going to move, what's the acceleration? And you know what to do. Acceleration is force divided by mass, so 50 divided by 100 equals 0.5 newtons. Now what will happen if I increase the mass? Same thing, same force, 100 kg. I'm gonna put another, let's say 50 kg on top of it, and then I'm pulling with 50 newtons. Same force but a bigger mass. What do you think gonna happen? Same acceleration? No, smaller acceleration, right? Acceleration is now since these two are kind of attached to each other, acceleration gonna be 50 force over mass. So 50, now the mass is going to be 150. So 1/3, which is 0.33 Newton. See? Meters per second squared. Meters per second squared. Acceleration drops. Okay, so instead of placing it on top of the bigger mass, I'm gonna attach it using I'm gonna glue the two masses together, so side by side. How about that? Now you see how convenient these boxes are. Imagine like you draw real world shapes, like you can as science students, biology or chemistry students, you will be dealing with forces applied on molecules or living cells. The diagram's going to be very, very tricky. Most of the times when it comes to molecular forces, we represent them using small circles. We don't draw the whole thing because it's too difficult to draw all these actual diagrams. We simplify them into circles and proceed. So the same thing, instead of a circle I use a box here. Easy to understand. So here we have this 100 kilograms. I'm going to glue this 50 to that, apply the same force, 50 newtons, same result, right? It will accelerate at 0.33. Now I'm going to make another change. Here's 100. I'm going to keep this 50 over here and connect them using a string. And then I'm going to pull it 50 newtons. Now what's the acceleration? These two are connected by a string. It's I would say a stiff or a rigid string, means it doesn't stretch. If this 100 moves, if this first box moves, the second box is going to move with it, right? It's not going to go with a different speed because the string is not elastic. It doesn't change the length. So question number 1, what's the acceleration? So for that, I'm going to consider this whole thing as a single unit, right? So it's like this. Make the string really, really short that they sit next to each other. You get the same answer. You can say F equals ma. The total force, the total net force you are applying is 50. There are tensions on the string. This little box is being pulled by the big one with some tension like this. But at the same time, the same tension is pulling back on this one. So when we think about the big system, these little internal stuff get cancelled out. When you consider the big system, right? The two tensions are inside the system, they cancel out each other. So we have F equals ma, force, the outside net force is 50, mass is 150 times acceleration, giving you acceleration equals 0.33 meters per second squared. Now I'm going to ask you another question. So let's say this is my rope 1, right, or string 1, or let's just say, yeah, S1. This is string 2. My question is, what are the tensions on each rope. So for an example, are they going to be different tensions, like tension 1 and tension 2, or are they going to be same? So how do we do that? Now, string 1, the first one, when you think about string 1, you are applying a 50 Newton. That 50 Newton is being transferred to this entire big system, right? So this force you are applying, this 50 Newtons, becomes the tension of the rope. So S1 is simply equals to 50 Newtons. What about the tension on S2? The tension on the small box, is it still 50 or is it something else, something bigger, smaller? How do we do that? So for that, we're gonna consider only the small box. 50 kilograms. There's a pulling force. This is our S2 string, and this pulling force, I'm gonna call it T2, tension 2. Now let's write F equals ma for this little box. The force is what I need to find out. So tension 2. The mass of it is 50. We know that this whole thing, the entire thing, both boxes moving at this acceleration 0.33, they move as a system. So the little box also has the same acceleration. So 50 times 0.33. So tension 2 is different from tension 1, little less tension, and the number is 50 multiplied by 0.33, which is equals to 16.5. Okay, that's the beauty of tension. Okay, the last example. So I'm gonna clear all this one more time. So we talk about, let's say, here's the horizontal surface, here's the box. We talk about applying a force like this, the mass, and then you do F equals ma and find the acceleration. We talk about applying a force like this. Let's say this is F1, F2. So we take the components using this angle theta. We take the components of this, and then using the parallel component or the x component, we can find the acceleration. What if we have two forces? In this case, one is F1 is parallel and F2 has some angle. What's the acceleration? Obviously it will be a little bigger than previous, because now we have more than one force. Earlier either it's just F1 horizontal or F2 at an angle. Now we have horizontal and a force with an angle, right? Together they'll combine and create a little bigger force. So how do we find that? So let's work with numbers right away. Alright, so here's the box, 100 kilograms, sorry, not newtons, 100 kilograms. Let's say we have an F1 force which is equals to 40 newtons, and we have an F2 force which is also 40 newtons. Actually, to make things simple, let me make it 30 so that you won't get confused. 30 newtons, and okay, so this time let's make it 25 degrees, otherwise too many 30s. Alright, so two forces acting on the same object. Question is, what's the acceleration? Alright, so what do? This F1 is already on x-axis. So I have told you guys earlier, if something is on either x or y axis, you don't change them, you just leave them as they are. F2 on the other hand is 25 degrees to the horizontal. So we're going to split F2 first. So that's our first step. We're going to split it. So here we have F2. Here's 25. So this direction I can write F2 cosine 25, which is 30 cos 25, which is 30 multiplied by cosine 25 equals to 27.18. 27.18 newtons. Now you can find the F2 sine 25 component as well. So it will be a small force, something like 10 newtons probably, and it's not going to do anything because it's not enough to lift it, so let's not worry about that. So on the object we have 40 newtons going this way. Also we have 27.18 newtons going this way. Two parallel forces, what do? We add them. So this gives us a single force of 67.18 newtons. Now we can write F equals ma. 67.18 equals 100 times acceleration. Acceleration divided to the other side, 0.67 meters per second square. Okay. So if you have multiple forces, you split them, take the components and add the components that are in the same direction. If they're in opposite directions, you subtract. So something like this. Right, you're pulling this way with 40, you're pulling this way with 30, making 25. So you still take the components, and now this x component 30 cos 25 is against this 40. So you subtract them and then use F equals ma. Alright. Okay, so that's a lot of examples. We will work on few problems in class as well. Alright. Thank you.